is we'd like to have you look at graphing exponential functions, and then we're going to look at their inverses. The first problem that I'd like to, there's two types of problems actually, that we're going to graph, and one is going to be an exponential growth equation, and the next is going to be an exponential decay function. So we're going to focus on exponential functions in this first area, and we're going to look at the two situations that you're going to see. One is exponential growth and the other is exponential decay. The equation that I'd like to graph with you right now is y equals 3 to the x power. And I'm going to ask you to watch for some particular things that happen as we graph this function, where what I call its base, the 3, is a number that's greater than 1. And we're going to talk about values for our base that work appropriately. There is no reason why I cannot put negative values in for x, and so I will consider putting in a -2 and a -1. I'll put in 0 for x, and I'm just going to try to put in a few ordered pairs into this expression. When I put a -2 in for x, what I have here for my output is 3 to the -2 power. Well, please remember that that needs to be written with a positive exponent, so that's the same thing as 1 over 3 to the +2 power, or 1 over 9. So think of that when I put negative exponents. I'm not going to be able to write it every time. When I put a -1 in for x, I have 3 to the -1 power, which is 1 over 3 to the +1 power, and I'm all done there. When I put a 0 in for x, 3 to the 0 power, anything raised to the 0 power is 1. When I put in a 1 for x, 3 to the first power is just 3. And when I put in a 2 for x, 3 to the second power, it means 3 times 3, or 9. And I'm going to go ahead and graph these ordered pairs now. So when I graph the first one, where x is a -2 and y is 1/9, I'm very close to the x-axis there. And I'm also quite close to the x-axis here when x is a -1 and y is 1/3, but I'll move up a little bit. When x is 0, y is equal to 1. So here's this point, the y-intercept of this graph. When x is 1, y is 3. So here's that point. And when x is 2, y is 9, and here's that point. Again, called an exponential growth function, and it is because it grows very rapidly, and in this case, it goes from the lower left to the upper right as it expresses that growth. I'm going to mark these points again. Here's our first, here's our second. Watch this point right here. This is going to be one we're going to be talking about quite a bit. That's the y-intercept of that graph, and we're all done. We've got an exponential growth curve representing y equals 3 to the x. Before we move on, I'd like to just recognize or talk about a few things. This value right here in this problem, which is the base, the 3, can never be equal to a 1. If you would just think about that for a minute. And if I had y equals 1 to the x power, I'd be asking you to take the number 1 and raise it to the first, and square it, and cube it, and raise it to the 4th power. And it doesn't matter what you do with the number 1, with x as an exponent, you're always going to get a result of 1. So that would be a linear equation. That would be a straight line. So I wouldn't have anything that's represented exponentially. So my base here is always going to be values that are greater than 1, or it's going to be values that are between 0 and 1, like fractions. We're going to represent them as fractions. And we'll never let this base be negative values, because if I had raised that to a fractional root, I'd be taking roots of negative values, and if my roots were even, I'd be getting imaginary numbers, and we're not going to go and look at the imaginary number system or complex numbers. So we're staying with bases that are positive. Those that are between 0 and 1 are going to represent exponential decay. Those that are greater than 1 are going to represent exponential growth. And then we're going to do a little bit with changing the exponent as well. The next function that we're going to graph, y equals 3 to the x plus 2 power, only differs from the last one, and the exponent is no longer just an x. It is x plus 2, or I'm going to raise this through 3 to that full power, if you will. So think of that as having exponents around it. So I decided to choose my first value for my independent variable x of a -3, because I'm going to put in here a -3 plus 2, and I'll have 3 to the -1. Well, we've said that that's the same thing as 1 over 3 to the +1, or 1/3. And when I put in a -2 into this expression, a -2 plus 2 is 0. Anything raised to the 0 power is always equal to 1. When I put in a -1 here and add 2 to it, I get a +1. 3 to the first power is just 3. And then when I put in a 0 here, 0 plus 2 is 2. 3 squared is equal to 9. And finally here I'll get a 27 because I'll have a 3 cubed. So I'll go over here and represent this on my rectangular coordinate system, and a little bit differently than before, but the shape itself is going to be the same. When x is a negative 3, y is 1/3. When x is a negative 2, y is equal to 1. When x is a negative 1, y is equal to 3. When x is 0, y is equal to 9. And I still have an exponential growth curve. I'm not going to graph the next point because it's too hard to see. So there's my exponential growth curve. But this time, rather than crossing the x-axis right here, it crosses way up here at 9 because I've altered my exponent a little bit. But one of the things I'd like you to notice now is both of the graphs that we've just graphed have never never crossed the x-axis, and they never will. This is called a horizontal asymptote. This graph of this function, again, will never come down this way. Matter of fact, if you were to do that for me on your test, I'm going to mark some portion off because I need you to recognize that there's a horizontal line. It's like an imaginary line that this graph cannot cross for this exponential growth curve. Now I'm going to do some things to it in a minute that will allow it to shift up and down a little bit. But for right now, my horizontal asymptote is right here. Again, an exponential growth curve because I have a 3 here rather than a number between 0 and 1, or a fraction. The next exponential function that I'd like to graph, again, very similar, 3 to the x power, but now I want to subtract a constant, 2. And you're going to see how we still have an exponential growth curve, but this curve is going to be shifted down because of that minus 2 that is represented as that constant. I'm going to choose these x values to put in for my exponent. They work fairly well, and that's why I work with them. They're going to give me some fractional values, but when I put a negative 2 in here for x, 3 to the negative 2 is 1 over 3 to the positive 2, or 1/9. And then I'm going to subtract 2 from that, and I'm going to get a negative 1 and 8/9. I guess that's the way I'm going to write it. And I'm going to erase this so it doesn't get in the way. Again, 3 to the negative 2 is 1/9. I subtracted 2, and I got a negative 1 and 8/9. When I put a negative 1 in here, I have 3 to the negative 1, or 1/3. Minus 2, so I'm going to get a negative 1 and 2/3 for that piece. Got to make sure I didn't, 3 to the negative 1, 1/3 minus 2, yeah, exactly. Next I'm going to put a 0 in for x, and 3 to the 0 power is 1. Again, anything raised to the 0 power is always equal to 1. 1 minus 2 is a negative 1. When I put a 1 in there, 3 to the first is 3, minus 2 is a positive 1. When I put a 2 in there, 3 squared is 9, and 9 minus 2 is 7. So I'm going to come on over here now and graph these points. So when x is a negative 2, y is really close to a negative 2, but a little bit higher. About right there. And when x is a negative 1, y is a negative 1 and 2/3. X is 0, y is a negative 1. Now it crosses the y-axis, that's the y-intercept. When x is 1, y is 1. And when x is 2, y is equal to 7. So I have a graph of this exponential growth curve, again, because this number right here is greater than 1. And what I'd like you to notice is that I'm going to have, right there, I'm going to have a horizontal, and I'm going to write that down here, horizontal asymptote, where y is equal to a negative 2 because of that value right there. I will not cross that point like in the past two problems where I had 3 to the x power. I never crossed this horizontal asymptote where y is equal to 0. I'm not going to go below that. This would keep going in this direction because 3 to any negative power, negative 5 for example, is 1 over 3 to the 5th. It's a very small number, and when I subtract 2 from it, I get something close to a negative 2, but not equal to a negative 2, so I'll never be able to get there. I'm all done. I've graphed this exponential growth curve. Here, watch my y-intercept. Yeah, I think that's it. We're now going to graph an exponential function where the base is no longer greater than 1, where the base is something that's between 0 and 1, and again, I just want you to see the difference. It's fairly dramatic. I'm going to start with 0 because it's easiest to put a value of 0 into this function. So I want you to see how quickly we can get these values at first. 1/3 to the 0 power, again, anything raised to the 0 power is equal to 1. When I put a 1 into this function, 1/3 raised to the first power is just 1/3. When I square that, I get 1/9. And when I cube it, I get 1/27. So you can see these numbers are getting smaller and smaller and closer to 0 all the time. Now, when I put a -1 in there for x, I have 1/3 raised to the -1 power. Well, remember, we've said that you can write that as 1 over that raised to the positive first. But when I divide this out, 1 divided by 1/3 is 1 times 3. So I get a value of 3 here. Be careful with that. It's fairly simple. Your calculator will certainly check it for you. When I put a -2 in there for x, I'm going to have 1/3 raised to the -2 power. The easiest way to do this is to just flip it, 3 over 1 squared now, no longer to the -2 power, but squared, and so I get an output here of a +9. So I go over here to graph this, and when x is a -2, y is a +9. I think I need that 1, 2, 3, 4, 5, 6, 7, 8, 9. So right there is my first ordered pair. When x is a -1, y is 3. Is my next value. X is 0, y is 1. When I have no constant added or subtracted to this expression, I am always going to cross the y-axis, the y-intercept at 0, 1, because that's when x is 0. This expression raised to the 0 power is always equal to 1. When x is 1, y is 1/3. When x is 2, y is a 9th. When x is 3, y is 1/27th, and all it does there is just approach and approach and approach the x-axis, but it never gets there. So when I sketch a curve in to these ordered pairs, it just gets close to this axis, but it doesn't touch it. So again, I have a horizontal asymptote, but this is the graph of an exponential decay curve. It starts high and comes down low and doesn't cross this horizontal asymptote, the x-axis, or where y is equal to 0, because I have 1/3. First of all, it's exponential decay, and I have no constant over here. That's why the horizontal asymptote is where y is equal to 0. That's all we'll do with graphing of exponential functions. We're often asked to graph or to take a look at the equation where we don't have y alone, but we have x alone. In this case, x equals 3 to the y power. This is going to come in handy when we talk about inverse functions, but for right now, I just want to look at how I would graph this function. Well, because x is alone and y is, if you will, with the other term on the right-hand side of this equation, I'm going to pick values for y to put into this expression to find out what x is equal to, and we're going to graph that curve. So if I put in, notice how I picked the base that we've been using right along, which is a base of 3. So when I raise y, or raise the 3 to a -2 power, 3 to the -2, remember, is 1 over 3 to the +2, or that's equal to 1/9. And when I raise 3 to the -1st power, I get 1/3. And when I take 3 and raise it to the 0 power, I get 1. And 3 to the first is 3, and 3 to the second is 9. And I'm ready to go ahead and graph these now on the rectangular coordinate system, just a little bit different than before. When x is 1/9, so now I'm talking about right here, I'm going to go hug this y-axis very closely, and y is equal to a -2, so maybe right there. And when x is 1/3, y is a -1. And when x is 1, y is 0. X is 3, y is 1. And the other point is way out here somewhere. X is 9, y is 2. And would you notice, rather than having a horizontal asymptote, where y, the x-axis, where y equals 0 is something you don't cross, in this equation right here, the y-axis is my vertical asymptote. The graph of this equation would come close and close and closer to the y-axis, but never touch it in this expression. This very curve right here would have looked like this. I'm just going to do a real quick sketch. If I had graphed on the same set of axes y equals 3 to the x power, it looked like this. And so all I want you to notice right now, for a minute, is the reflection of these two curves across this line right here. If I would take a piece of paper and fold it, and say this was an ink right here, wet ink, and fold it along that line, this curve would be that curve. And that's going to be, in our next topic, the topic of inverse functions, the definition. We switch the x and the y values, and that's what I've done right here. But anyway, here's the graph of x equals 3 to the y. Here's the graph of y equals 3 to the x. They are called inverse functions, and they are reflective across this line, which is called the line that represents y equals x. Every ordered pair on that line, the y value and the x value are equal. Look at that right there. Again, just trying to get you to see those points. The last concept to discuss in this section is applications of exponential functions. And there are several that are presented, but the only one that I'm going to look at with you is the situation where we invest some amount of money that earns interest that's compounded annually over some period of time. The equation that represents that is a equals p times, in parentheses, 1 plus r to the t power, where a is the amount in an account that you have after a period of time because you put it in an investment. P is the present value that you're going to invest in that account. R is the interest rate compounded annually that the banker is going to give you, and T is the period of time with which you're going to invest that money. Well, one of the problems, and there's quite a few actually in our text, ask us to, let's say, invest $50,000 compounded annually at an interest rate of 8%. Over time. And what we'd first like you to do is to write a function that represents that situation. Again, $50,000, $50,000 invested right now at an interest rate of 8% over some period of time. So if I want to write a function for this, all I'm looking to do is substitute in for P and for R these values. So I would have A equals 50,000 times 1 plus 0.08 is how I write that interest rate. I don't leave it as 8 raised to the t power, and I clean that up a little bit, and I would find out that I just need to take $50,000 times 1.08 to the t power, t representing time in years, to find the value of that account over time. So let's say that I chose then to substitute in, let's go with 0 years and 1 and 2 and 4 and 8, maybe 10. Let's go that far. Let's put those values in for t here in our calculator. Now I need to do that in my calculator so I can find out A, which is the amount that's in the account after that period of time. So after 0 years means now. That's what that means. So what's in that account now? Well, 1.08 to the 0 power, anything to the 0 power is 1. So 50,000 times 1 is 50,000, and that seems very clear that I've got $50,000 in that account right now. Well, when I put 1 in for t, 1.08 to the first power is just 1.08, and when I multiply that by $50,000, I have $4,000 in interest added to that $50,000. So now I have $54,000 at year's end. Now, it doesn't mean that I'm going to have $58,000 after 2 years because I earned $4,000 in the first year. Now, because I'm going to earn interest on that interest, I'm going to earn interest on this whole amount. By putting a 2 in here, you have to use your graphing calculator, 1.08 to the second power, whatever that is, multiply it by $50,000, you get $58,320. So compounding our interest annually in this case earned us a little bit of extra interest over and above the first year where we only earned $4,000. This year we earned $4,320. We go ahead and keep up with this process, and now we have $68,024. I'm going to drop off the cents for time's sake, and we get to $92,546. It's 51 cents, so I might call that 7. Mind you, this is 8 years later. This is not just a year at a time that I'm going now. And after 10 years, we have $107,000, $946, again, in some odd cents. And money grows exponentially. This is a great application of this situation that we've been studying. Now, if I were to graph this, and I'm not going to graph it carefully, I just want you to know that it would start up here at $50,000, and it would grow like that. Now, I'm exaggerating it a little bit, but that's what the graph of this data would be like if I graphed this point in 1 year, and 2 years, and 4 years, and 8 years, etc. Good application, very good application. I have put some problems for you to solve in Course Compass that involve the growth of bacteria. I believe also the growth of insects like mosquitoes. Actually, that's probably the one I have. And the other exponential growth problem, no, I don't have another exponential growth problem. I have two decay problems. The decay of a car, the value of a car, I'm sorry, and the decay of medicine that's in a gymnast's body over a period of time. So they take medicine right now, and that decays, and it decays in terms of the amount that's in their body, till there's a residual amount left over, and it's finally, eventually, some point later, nothing left in their body.